I'm Andrew G. Delector that will show you a sample problem and how to solve it. A counterflow cooling tower with 30 inches of cellular fill was designed for an approach of 10 degrees Fahrenheit and a cooling range of 17 degrees Fahrenheit when the wet bulb temperature is 75 degrees Fahrenheit. The tower cross-section is 36 times 36 in feet, and airflow and water flow rates are 523,000 cubic feet per minute at 90 degrees Fahrenheit and 6,000 gallons per minute. Letter A. What are the inlet air enthalpy and the change in the enthalpy across the tower? Letter B. Calculate the number of transfer units and the height of transfer unit for this condition. Letter C. How much more fill would be needed if the wet bulb temperature were 78 degrees Fahrenheit and the desired approach were 7 degrees Fahrenheit? This problem is also problem 19.3 in McCabe 6th edition. To solve the problem, we must first draw the figure, put in the necessary variables, and define these variables, which is now shown to you. We solve for the unknown values of the different temperatures, because these are needed later. To solve for the outlet water temperature, we use the approach, which is defined as outlet water temperature minus the wet bulb temperature. Thus, we get TL2 to be 85 degrees Fahrenheit. The inlet water temperature can be known through the range, which is defined as the inlet water temperature minus the outlet water temperature. Thus, we get TL1 to be 102 degrees Fahrenheit. Before we continue, we must first write what are the requirements in the problem, which are A. Change in enthalpy across the tower, B. Number of transfer units and height of transfer unit, and C. The height of additional fill if wet bulb temperature is 78 degrees Fahrenheit and approach is 7 degrees Fahrenheit. Now we go for the solution proper. For letter A, enthalpy can be determined, hence adiabatic saturation temperature is just equal to the wet bulb temperature. We can get the value of the inlet air enthalpy HV1, outlet water enthalpy HL2, and inlet water enthalpy HL1 from figure 19.8 using the equilibrium curve and their respective temperatures. Values are as shown to you. The density of the vapor, ρV, can be calculated by the equation ρV is equals to molar mass of air over specific volume of air at standard temperature and pressure, multiplied by the standard temperature over the inlet air temperature. Since other variables are already given or computed aside from a specific volume, we solve for it. A specific volume can be determined from reciprocating density constants or from humidity chart as from figure 19.2 from McCabe 6th edition. Variables will be converted if necessary to get pounds per cubic feet density value. Vapor mass flow rate per area G prime V can be determined by equating it to vapor volumetric flow rate V dot V over the given area and multiplying by the calculated raw V. Liquid mass flow rate per area GL can be determined by equating it to liquid volumetric flow rate V dot L over the given area and multiplying by the calculated raw V. GL is equals to 2317.1373 pound per hour feet squared. Unit conversions was done for unit consistencies. Some of you might wonder why there is a constant vapor and liquid flow rate, when previously it has been discussed that there's evaporation losses, losses of spray droplets, adrift, and etc. But according to McCabe, This accounts for only 0.2%, which he assumed negligible, in a well-designed tower. To get the required change in enthalpy across the tower, we use equation 19-27 of McCabe 6th edition, taking note that specific heat of liquid Cl is 1 BTU per pound degrees Fahrenheit. Thus, change in enthalpy across the tower is 22.5622 BTU per pound. For letter B, we solve for outlet air enthalpy. Then we solve for the change in enthalpy at the top of the tower and the bottom of the tower, and we get the mean of this change in enthalpy. To get the number of transfer units, we just divide the change in the enthalpy across the tower and the mean enthalpy change at the top and bottom of the tower. Height of transfer unit can be solved by dividing the field height by the number of transfer units. Thank you for listening, and here is Miss Colleen Meir to solve further.
Hi, this is Bonifi Colleen Meir to further discuss sample problem number 1 and to discuss sample problem number 2. For the last part of sample problem number 1, we are asked to find how much more fuel would be needed if we are given the wet bulb temperature equal to 78 degrees Fahrenheit and the approach value equal to 7 degrees Fahrenheit. At the wet bulb temperature 78 degrees Fahrenheit, we could get the value of HV1 equal to 34 BTU per pound. And from the given approach, we'll arrive at TL2 equal to 85 degrees Fahrenheit. From the values of A, we have TL1 equal to 102 degrees Fahrenheit, the range equal to 17 degrees Fahrenheit, and delta H is equal to 22.5017 BTU per pound. Delta H is equal to HV2 minus HV1. Since we are already given with delta H value equal to 22.5017 and HV1 value equal to 34, we could get the value of HV2 and it is equal to 56.5017 BTU per pound. So on top of the tower, we have HL1 minus HV2 equal to 68 minus 56.5017 equal to 11.4983 BTU per pound. And at the bottom of the tower, we have HL2 minus HV1 equal to 42 minus 34 equal to 8 BTU per pound. Therefore, our H star minus HL is equal to 11.4983 plus 8 divided by 2, and the answer is 9.7492 BTU per pound. So to get the number of transfer units, N, we divide HV2 minus HV1 by H star minus HL. We have 22.5017 divided by 9.7492. The answer is 2.3081. For the height of the transfer unit, we use the formula H equal to fill over N. So to get the value of fill, we multiply H by N. So fill is equal to 3.9. Since 3 feet is available already, approximately an additional foot of fill is needed. To summarize all the answers in sample problem number 1, for letter A, HV1 is equal to 31 BTU per pound, and delta H is equal to 22.5622 BTU per pound. For letter B, we have N equal to 1.7739, H equal to 1.6912 feet, and for letter C, approximately an additional foot of fill is needed. Let us now proceed to sample problem number 2. For the cooling tower described in sample problem 1, predict the effect of increasing the air rate by 20% with the same liquid rate and the wet bulb temperature of 75 degrees Fahrenheit. For the given, we are to use the same cooling tower description with sample problem 1. For the required, we are asked to find the effect of increasing air rate by 20% with the same liquid rate with a wet bulb temperature equal to 75 degrees Fahrenheit. For the solution, we are already given with G prime V equal to 1745.9030 pounds per hour feet squared. That is from sample problem number 1. To get the new G prime V, we multiply G prime V with 1.2 and the answer would be 2095.0836 pounds per hour feet squared. Note that the new operating line has a lower slope, which increases h star minus hv. If n is about the same, TL1 will increase to give a lower value of h star minus hl. In this problem, we need to assume a value of the range. The guess range for this problem is equal to 19 degrees Fahrenheit. From that guess range, we'll find the value of TL2 that is equal to 83 degrees Fahrenheit. And from the value of TL2, we'll find the value of h star L2 equal to 40 BTU per pound. To get the value of delta HV, we use the formula delta HV equal to GL CL delta T all over G prime V. That is equal to 2317.1373 times 1 times 19 divided by 2095.0836. The answer for delta HV is equal to 21.0138 BTU per pound. Delta HV is also equal to HV2 minus HV1. And since we are already given with the value of delta HV equal to 21.0138 and HV1 equal to 31, we'll get the value of HV2, and that is equal to 52.0138 BTU per pound. At the bottom of the tower, we have h star L2 minus HV1 equal to 40 minus 31 equal to 9 BTU per pound. At the top of the tower, we have h star L1 minus HV2 equal to 68 minus 52.0138 equal to 15.9862 BTU per pound. So h star minus HL is equal to 15.9862 plus 2 divided by 2, and the answer would be 12.4931 BTU per pound. To get the number of transfer units, that is N, we divide delta HV divided by h star minus HL equal to 21.0138 divided by 12.4931, and that is equal to 1.6820, which is approximately equal to 1.7. So since N is approximately equal to 1.7, the exit water temperature should drop about 2 degrees Fahrenheit to 83 degrees Fahrenheit. So the effect of increasing the air rate by 20% is the exit water temperature drop of about 2 degrees Fahrenheit. Let us take note that, according to McCabe, in practice the value of approach is between 5 to 15 degrees Fahrenheit and the value of cooling range is between 10 to 30 degrees Fahrenheit.